Good morning, everyone. My name is Oindrila Ghosh. I am a second year graduate student in environmental engineering at UMBC. Today, I wish to share with you my work on the understanding of the time integration aspect of passive sampling. Passive sampling, as we all know, is an emerging method of sampling hydrophobic organic contaminants or HOCs in the environment. This work is a joint effort with my colleagues at UMBC, Dr. Songjing Yan, Mandar Bokhare, and my supervisor, Dr. Upal Ghosh. So here is a conceptual diagram showing how actual water column concentrations of HOCs vary over time, which is shown by the blue line, with events like storm flow, industrial runoff, and tides. The red line corresponds to the passive sampler based water column concentration of the HOC, showing the time integrated measurement of it. Now, passive samplers can provide the time integrated measurement of the concentration of an HOC in the dissolved phase that is actually bioavailable to the organisms in the environment. This aspect of passive sampling comes really handy for doing ecological exposure assessment. So for our study, the aim was developed from this context as mainly to answer the question of how well do passive samplers, or what does time integration actually mean for an equilibrium passive sampler like polyethylene. We came across this paper of 2009 conducted by Hawker et al. Uh, and this paper established that the analytically solved response curves of passive samplers, which are the solid lines that you see, they capture the characteristics of the variation of ambient concentration when it follows a linear or exponential or a pulsed function. So for our study, we tried to look at the impact of a single 10-day long pulsed perturbation in the freely dissolved ambient concentration of the HOC polychlorinated biphenyls or PCBs. And we wanted to see its impact on the uptake in an equilibrium passive sampler like polyethylene. And we assumed that because of the perturbation, there was a dilution in the ambient concentration from 10 nanogram per liter to 1 nanogram per liter. We estimated the actual mass of PCB uptake into the polyethylene, and then corrected it for equilibrium by a factor equal to the fractional loss of a known concentration of the same PCB from PE to water. And then we converted the mass of PCB accumulated in PE to an equivalent mass in water by using the right partitioning coefficient. The accumulation profile of PCBs into PE was modeled by solving the fixed diffusion equation numerically. The fixed diffusion model, it has two second order differential equations as the governing equations. The first equation controls the diffusion in the PE side, which are the mud colored sections in the schematic that you see. The second equation controls the diffusion in the water side, which are the blue colored sections that you see. And the third equation is a combination of two equations, and it holds true at the interface of the PE and water sections. The pink cell is nothing but a mass conservation cell, which is keeping the time loop going for the next iteration in time. So for our first simulation, we are looking at how the day of the introduction of the pulse in ambient water concentration impacts the rate of PCB uptake in passive sampler. And the first diagram to the top left shows how the actual water concentration varies with time. When the 10-day long pulse starts on the 20th day, the concentration goes down from 10 to 1 nanogram per liter and then goes back to 10 nanogram per liter post the perturbation. So regardless of the starting day of the pulse, the time average concentration stays constant at 9 nanogram per liter, which is represented by the purple bars to the right. And this is because the number of days, regardless of the day of introduction, is 10 out of 90 days of exposure. The bottom left diagram shows the accumulation profile of PCB37 into PE in normal condition versus perturbed condition when the pulse starts on the 20th day. And in the bar plot, we see that when the pulse starts on the 10th day, the concentration of PCB37, shown by the blue bars, is overpredicted by around 10%, because the sampler has enough time to equilibrate post the pulse and loses its memory of the pulse. But when the pulse happens shortly before the end of the exposure, the influence of the pulse is still in the memory of the sampler and is actually underpredicted by around 30%, say on the when the pulse starts on the 80th day. So a crossover happens from being overpredicted to underpredicted for PCB37, and the day of crossover for PCB37 is around the 60th day. So which means that the time period of integration, which is the amount of time that PCB37 requires to recover from a 10-day long pulse perturbation, is around 90 minus 60, around 30 days. So now the question is, how consistent is this behavior across the various PCB homologs? So we looked at 9 PCB congeners that are listed in ascending order of molecular weight and hydrophobicity here. Kpw, which is the partitioning coefficient of an analyte in PE with respect to water, and diffusivity of an analyte in PE or water are the functions of the hydrophobicity of a congener and molecular weight respectively. So the uptake kinetics is really a function of both the partitioning coefficient as well as the diffusivity in water and PE. So if you see in the no perturbation state, which is the diagram on the bottom left, the lower congeners reach equilibrium much faster than the higher congeners. PCB4, for example, reaches equilibrium in less than 10 days, while PCB128, which is the magenta curve, reaches only 25% of the actual ambient concentration in 90 days. The lower homologs are also more sensitive to the perturbation, as seen in the diagram to the right, and which is why for the same pulsed fluctuation in the ambient concentration on the 70th day, PCB4 has a much deeper dip than PCB128. If we think about it now, a 10-day long pulse thus renders constant time average concentration regardless of the day of the pulse. But the day of the introduction of the pulse and the hydrophobicity of the congeners are both quite active determinants of the predicted water concentration of a given analyte. So we wanted to look at our observations more concisely and do a quantitative measure of it. So we looked at the impact of both these variables of congener hydrophobicity and the starting day of the pulse on the uptake kinetics. And in the bar graph, we see that for a dihomolog like PCB15, when the pulse starts on the 60th day, represented by the orange bars, the concentration is overpredicted by about 10%, versus when the pulse starts on the 80th day, which are the violet bars, it is underpredicted by about 75%. But PCB128, on the other hand, which is a higher homolog, is more resistant to diffusive fluxes, and the percentage of over or under prediction of water concentration is quite low. We wanted to quantify the sensitivity of the congeners to perturbation and look at all this information in one diagram. So we correlated the time period of integration with congener hydrophobicity, which is the log KOW, and represented the degree of sensitivity of the congener with the radius of the bubbles. So while a congener, which is the second diagram to the right that you see, so here you see that while a congener of log KOW of 4.5 requires just 2 weeks to recover from a pulsed perturbation and is very sensitive to the fluctuation, a congener of log KOW of 6 needs at least 36 days, but is about 94% less sensitive to ambient perturbation in concentration. One of the things that provides resistance to the diffusive flux into the sampler is the thickness of the sampler itself. There are three major thicknesses of PE that we use for passive sampling. The 25 micrometer PE thickness corresponds to the 1 mil PE, and PCB37 reached equilibrium slower and experienced a lower dip due to the pulse for the thickest polymer, which is the 3 mil polymer. This information is also more concisely put in the second diagram, where we correlated the time period of integration with PE thickness, and the time period of integration varied from 31 days for a 1 mil PE to 38 days for a 2 mil PE and 40 days for the 3 mil PE. And the thicker polymer was also about 12% more resistive to perturbations in the ambient concentration, as is seen by the size of the bubbles. So in conclusion, for our study, we looked at an oversimplified version of ambient perturbation in concentration and the effect it has on the time period of integration of various PCB homologues. We could establish that the minimum amount of time that is required by a congener to represent the true water concentration is dependent on a couple of things: the nature of the perturbation, the hydrophobicity of the congener, and the design of the sampler. So for a 10-day long pulse, the range of time period of integration varied from around 14 to 15 days for a di homologue and about 43 to 45 days for a hexa homologue. Now, based on the site and the congener of interest, the design of the sampler can be toggled with to achieve the most efficient measure of the true concentration. One of the things that needs to be kept in mind, though, is the error associated with the PRC corrections for a higher homologue group or a thicker polymer. So based on the requirement of a particular study, these trade-offs need to be weighed in order to determine the most efficient sampler design for the congener of interest in a given perturbation scenario. With that, I would love to thank everyone for your time, and I hope to hear from you if you have any questions. Thank you.